So before I start, are there any questions? Okay, I will do that. Any other questions, requests, anything? Okay. In terms of logistics, I'm still hunting for a room. Apparently, there is a university regulation for makeup classes. They won't assign a room for the first 2 weeks, so I'm still kind of struggling with that. So the makeups would be there. Watch out. It may even be tomorrow. My department says that I'll have something tomorrow. So again, I'm going to record things. If you cannot make it, that's fine. But if you can come in, it would be good for me to have an audience also as I speak. So, and likewise, the same thing for next week. Because I'm missing the Wednesday lecture and Monday is a holiday, so I'll again do kind of a makeup. So just keep an eye on postings on Piazza. Let's see. I guess the other bit of logistic is just to put Salma on the spot. So our other TA, she's back from Egypt, thanks to U.S. Embassy. She got her visa now. So I guess Salma, you are handling the last discussion section, right? Okay. So those of you who are in section C, she's your TA, and her office hours are on Wednesdays 1 to 2, right? Yeah. Okay. So Wednesdays 1 to 2. So in any case, no one is showing up in office hours. So I guess at some stage we'll get bored and stop coming too. But that's probably not good. So try to come if nothing else. Chat. Maybe I can help you with, I don't know, other things. You have your resumes to run by. Treat me as an informal advisor, whatnot. But just I think it's a good idea to have a connection with your instructor and TAs. So even if you have nothing to do, drop by. We are there. Okay. So, Minter, Maxterm, I realized kind of there was a lot of stuff towards the end last time around. So, again, I'm going to go through some of it, not necessarily to the same level of detail. So, Minterms and Maxterms, these were two concepts that we had introduced. Okay. So, these are just definitions, okay? So there's nothing magical about it, but as we'll see, they kind of play an important role. So if I have a function with a bunch of inputs, so some combinational function, and in this particular case, inputs A, B, and C, then a minterm is nothing but an expression which consists of a bunch of ands or conjunctions, so that's the upside down V, and such that every input appears in that expression, and either in its positive form like A or in its negative form like not A. So each one of these are examples of minterms, and since any input can appear either in positive or negative form, so there are two choices, and if I have n inputs and I need to have each one of them, so therefore there will be 2 to the power n distinct possible minterms that exist. And so it's just ANDed expressions, and again the key thing is every input has to appear. So for example, for this particular function, A and B will not be a minterm because it would be missing C. So that's kind of an important thing to remember. And Maxterm is a similar concept, except in this particular case, instead of and, we have or disjunction in a more formal sense. Okay, so again, each input must appear. They should be ORed together, and the input can be either in a positive form or a negated form. So this is just definition. And another bit of definition that we had last time around was that to represent, to refer to minterms and maxterms in a compact way, there's a numbering scheme which is assigned, and there are sort of many different ones which float around in the literature, but the one I'm describing is kind of the more common one. And I believe it differs from the one in the textbook, but this is a more common one, so we're going to just stick with that. And kind of the idea is the following. So if I give you a combinational function, so in this particular case, now I have picked a function with 4 inputs, A, B, C, D. The first thing we do is we give those inputs in order. Okay, so in this particular case, the order I have given to them is D, C, B, A. And then we think of this DCBA, so just imagine kind of a 4-bit number. The 1 bit is D, the leftmost, the next one CBA. So D has the highest weight, the highest value, and A has the lowest value. So it constitutes a 4-bit number, and we think of it as now as a 4-bit number. So DCBA can go from 0 through 15. Those of you don't recall your sort of binary things or have never seen it, it kind of works like base 10, so except that this is base 2. So things, bits which are rightmost have a weight of 1. The next one is a weight of 2, then a weight of 4, and then a weight of 8. So for example, 0, 1, 1 is 4 plus 2 plus 1. And in the 8th position, the weight is 0, so that adds up to 7. So that's why it's the number 7 out here. And likewise, 1, 0, 1, 1, in the 8th position, there is a 1, so that's 8. There is a 0 in the 4th position, so we don't get any contribution. In the 2th position, there's a 1, so that's a 2, so 8 plus 2, 10. And then finally, in the 1st position, is a 1, so we end up at an 11. Okay, so we order these inputs and then start thinking of and consider all possible values and think of them as a binary number. And so they'll go from 0 through 15 in this case because I have a 4-bit number. And then what we do is we list the minterm and maxterm in the order which is shown. And kind of a trick out here is the following, that for minterms, if I have a minterm, so if I'm looking at row which is labeled 100, 1000, then I would, in the corresponding minterm, wherever I have a 1, the corresponding input will appear in a positive form, and wherever I have a 0, the corresponding input will appear in a negated form. So for example, 1000 corresponds to D being positive because I have a 1. Next one, C, B, and A all being in negated form. So D and not C and not B and not A. That's a minterm. Likewise, if I look at, let's say, 1100, then that is, as you can see, D and C because the first two are 1s, next two are 0, so it's not B and not A. So again, this is just a convention. So we basically say we consider all possible 16 cases and map them to a corresponding minterm. And then we basically say that this particular minterm has the index number, whatever is given out here. So D and C and not B and not A because it corresponds to 1100, whose numeric value is 12. So therefore we say it is minterm number 12. And the example I have is minterm number 2. It's not D, not C, B, A, and not A. So that corresponds to 0010, which has a numeric value of 2. So again, just a convention, 16 minterms, 16 rows, we map minterms to a corresponding row number. And the same story for maxterm, except the trick out here now is that wherever I have a 1, the corresponding input appears in a negated form, and wherever I have a 0, the corresponding input will appear in a positive form. But of course, since it's a maxterm, it's an ORing. So if I look at, let's say, 1010, whose numeric value is 10, the corresponding maxterm is not D because I have a 1 in the D's position, or C because there is a 0 in the C's position, not B because there is a 1 in the B's position, and then finally A. So not D or C or not B or A. And so again, for each one of the row, I'll have a unique maxterm, and we label the maxterms by the row number. So the M6 being an example. And minterms are labeled with a small m, and maxterms are labeled with a uppercase M. So again, all of this is just definition and conventions. I mean, that there's a compact way. So instead of having to write this big expression, I can just say small m, the index number, or big M and the index number, and that kind of tells me the minterm and the maxterm. And we'll see in a bit that it kind of helps write expressions in a more compact way. Now, of course, for it to make sense, for any numbering scheme to make sense, it's important that we all agree to a common numbering scheme. Okay, I mean, it's possible that there might be some different ones. Sometimes in the books you may see that max terms start from the bottom up. So the bottom one would be called big M of 0 and goes up. But again, that's convention. There's nothing right or wrong about one or the other as long as we are consistent. And I guess in this course, you have to use the scheme that I am presenting. So any questions on this one? So min term, max term, and numbering. Okay, just definitions and conventions. Okay, so next thing then. So what these min terms and max terms play a role in is something called a normal form of a Boolean function. So normal form is a standard term in mathematics which basically says a standard way of representing something. So kind of the idea is that if I have a combinational function, then there are many different logic expressions which correspond to the same function. They'll have the same truth table, same mathematical reality. Given an input, they'll give the same output. So if I give you two expressions and I say, are they representing the same mathematical function? Well, when you look at the expression, they may look quite different, even though when you plug in the inputs, they'll give the same output. So one way of comparing whether two functions are actually the same, two expressions are actually representing the same function, is to write both of them in a standard form. And that is what is called as a normal form. And it turns out that there are two standard forms which are used very commonly in digital logic or Boolean logic. One is called disjunctive normal form, or sum of products. And kind of the idea here is that a function is represented by taking a bunch of minterms and ORing them together. Remember, minterms was ANDing of input terms, and now we are saying the function itself is ORing of a bunch of minterms. So as an example, f of a, b, c could be written as the minterm a and b and c, ORed with the minterm a and not b and not c, ORed with the minterm a and not b and c. So this this is, as you can see, there are three terms ORed together, and each term is a minterm because in each term we have an ANDing, and all the inputs are appearing either in positive or negative, either in a normal standard form or negative form. So this is a disjunctive normal form representation of this particular function. There is a corresponding kind of a dual of it, which is called conjunctive normal form. And in this case, I have a bunch of max terms, and they are ANDed together. And an example of this is FABC written as three ANDing of three terms. So I have three terms. First term is A or B or C. This is a max term. The second term is A or not B or not C. That's also a max term. And the final one is A or not B or C, which is also a max term. So we'll see that given a mathematical function, the set of minterms, if you're using the first one, that it depends upon is unique. Okay, and we'll see shortly where it comes from. Okay, and likewise, a set of max terms is also unique. So the only difference that will remain is the order in which they appear, but the set would be unique. Okay, so just bear with me on for a moment on that one. So again, thus far we are saying, so anytime I see a function, anytime I see an expression which is written as ORing of minterms, then we say that is a function, whatever function it is, we have written it in a disjunctive normal form. And likewise for this one. Go ahead.
So ignoring reordering of terms, is there only one normal form for truth table?
That is correct. Because truth table is the mathematical reality, right? It basically says for each possible input, what's the corresponding output. So if I give you the truth table, and then I say corresponding to that truth table, let's say what is the disjunctive normal form, then ignoring the ordering part, it would be unique. Okay. And intuitively, what is, okay, so yeah, one other thing, if it just says normal form, is the first one. Okay, so that's kind of now let's go to the uniqueness part. So, so the way it kind of comes is the following: that how do we come up with the two normal forms? So, this is a truth table corresponding to the example sort of we've been using, the digital thermostat. So, what we have is we have four inputs, 2 bits of current temperature, 2 bits of preset temperature, and then we have an output. Okay, and it really kind of doesn't matter that it happens to be digital thermostat, could be any function. Point is, given a mathematical function, I can express it as a truth table, an exhaustive listing of inputs and the corresponding output. And what you would see is that so for the output is going to be 0 for some rows, 1 in some other rows. Okay, and one way of saying is that you can say, okay, when is the output 1? Well, one way of expressing that fact is that the output is 1 whenever input corresponds to, in this particular case, row 1000 or row 1001 or one of the final 4 rows, right? So one way of saying that when is this output, when is this function 1 is saying the input correspond to, uh, let me see what the row numbers are. So 0, 1, 2, okay, so we are going 1, 0, 0, 0, so that's row number 8, row number 9. So we are basically saying if my inputs are such that I'm either on row number 8 or row number 9 or row number 11, 12, 13, sorry, 12, 13, 14, 15. If I'm on one of these rows, then the output is 1, the function is 1. So essentially what we are saying is that output is equal to 1 if inputs correspond to row number 8 or input corresponds to row number 9 or input correspond to row number 12 or input corresponds to row number 13 or row number 14 or row number 15. And each one of these facts, when I say input corresponds to row number 8, that is equivalent to saying that the min term corresponding to this has a value 1. Right? So so let's look at so let's say we were to label A as A1 A0 and B as B1 B0, then saying that my input is 1000, that is I am in row number 8, is the same as saying that the expression A1 and not A0 and not B1 and not B0 has the value 1. Is that point not obvious to anyone? So again, the statement that inputs correspond to row number 8, which let me mark it, just give me a sec. So I'm looking at this one. So I'm considering this row. So the statement that inputs correspond to row number 8 is the same as saying that this expression has a value 1. That is A1 equal to 1 and A0 is 0 and B1 is 0 and B0 is 0, which is equivalent to stating that that min term takes on the value 1. And I can do the same thing for every row. So so the statement that output equal to 1 is the same as saying the inputs are in a row 8 or row 9 or row 12 or row 13 or row 14 or row 15, and each one of them corresponds to a particular min term. And that's what we end up out here. We are basically saying M8 means min term number 8 takes on the value 1, which is another way of saying is that the inputs are such that they correspond to row number 8 of the truth table. M9 likewise says that min term number 9 is true, which is another way of saying is that inputs are such that I am in row number, they correspond to row number 9 of the truth table. That is, inputs take on the value 1001, and so on and so forth. So the approach out here is you look at the rows which correspond to the 1 output, and then we are basically making kind of a logical statement that function has the value 1 if inputs correspond to row number I or row number j or row number k, where those rows are the one where the output takes on the value 1. If inputs are such that they correspond to a row where the output is not 1, let's say input was 0, 1, 0, 1, then each one of those minterms will have a value of 0. And so I will end up with an expression 0 or 0 or 0, and that would have the value 0. So anytime, so given a particular input value, if it corresponds to a row where the output is 0, then each one of the minterm in this expression would be 0, and the ORing a bunch of zeros all together is also 0. False, false or false or false, that is logically false also. And if the input happens to be such that it takes on one of the rows, it corresponds to one of the rows where the output is 1, then one of those minterm will be 1. The others are going to be 0. And so we end up with an expression 0 or 0 or 0 or 1 or 0. So a bunch of zeros and a 1. And when we OR them together, we'll end up with a 1. So in either case, it's going to work out. So I guess going back to question which was earlier on, that is this type of a normal form unique? Well, it has to be unique because a given mathematical function will have a unique truth table. And our way of coming up with this is that we are focusing on the rows where the output takes on the value 1. And therefore, there has to be kind of a one-to-one correspondence out here. Any questions on this one? So in a compact way, we can kind of write this thing in this particular way: sigma m, and then within parentheses, you just list all the minterms which have to be which correspond to those rows where the output takes on the value 1. So in this particular case, 8, 9, 12, 13, 14, 15. And so this, go ahead.
So when you say minterm 8 in this case, that's like you take the bits from A and bits from B and you concatenate them?
That's what we are doing. So we are thinking of, because remember, that's how I've written them out here. So very first bit corresponds to A1, the next bit of A corresponds to A0, and likewise B1, B0. So I'm thinking of A1, A0, B1, B0 as a binary number. Okay, and then if you look at 1, 0, 0, 0, that means A1 is 1, A0 is 0, B1 is 0, B0 is 0, and that's the number 8. Okay, and you could reorder them and have a different numbering. You'll end up with a different numbering, but you will still have, in this particular function, 6 rows which have a value 1. So there will always be 6 minterms. Depending upon your numbering scheme, the numbers here may differ. But for any given numbering scheme, you are going to end up with something which looks like this.
Also, so these minterms and maxterms should only be true or false for a specific value, respectively, right?
Correct. So given a function with some k inputs, I have 2 to the power k minterms. 2 to the power k possible minterm expressions. But in a representation of that function, in the logic expression which corresponds to that function, not all minterm will occur. Only those minterms occur which correspond to the rows where the truth table was taking the value 1. Okay. So staring at this, the other thing you can look at is the following, that whenever I'm writing a function in this canonical form, then I basically have minterms. I am doing a ORing of minterms. Each minterm can occur or not occur. So I have 2 choices. And how many minterms do we have if I have a function of k inputs? 2 to the power k, right? So I have 2 to the power k possible minterms, and each minterm can occur or not occur. Therefore, how many functions can exist? 2 to the power k. So so looking at this, if I'm looking at all functions that can exist with 4 inputs, right? I have 4 inputs out here, all functions with 4 possible input bits, then this is one such function. But I have and I have 16 possible minterms. Each minterm can occur or not occur, and therefore I have 2 to the power 16 such 2 to the power 16 4-bit functions that exist. Okay, and that kind of makes sense because if I draw the truth table, there are 2 to the power 16 possible distinct truth tables where I have 4 bits of input. So each row you can think of can take the value 0 or 1. So like, for example, there is a trivial function where the output is always 1. And another trivial function where the output is always 0, right? I mean, these are, so the function where output is always 1 corresponds to sigma m 0, 1 through 3 through 15. Sorry, if the output is always 1, yeah. And if the output is always 0, then it's basically the vacuous function. It doesn't have any, no minterm occurs in its normal form.
So we probably want to simplify this in some way, but is there like an estimate you can make as to the complexity of a circuit based on how many minterms or maxterms?
Yes, you can have it correspond to the number of gates, and you will be doing that in the course. Okay. And by the way, the other thing is, again, remember, this is just a standard form. It doesn't mean that this form is the most efficient. In a real circuit, you'll probably not use implement things in the standard form. Okay, there might be more compact way of representing things, or one with fewer gates, or faster, or lower power, or cheaper, or smaller area. Any number of things. But the only the one nice thing about this is that this is a standard way. So, I started with a truth table. I had an expression. You started with a truth table. You have a different expression, but they represent the same truth table. So if I give you 2 expressions and say, are they the same? It might not be obvious algebraically, how do I go from one to another? But if I convert both of them to the standard form, then I will have a standard way of, I would be able to compare them, because then only the order matters. And dual of this is the Maxterm form. And the way the Maxterm form works is the following. So again, it's the same truth table. This time around, I focus on when the output takes the value 0. And kind of the idea is that, I'm basically trying to see when is this function 0. And one way of stating that is, this function is 0 if, and I look at all the rows which correspond to 0 and then AND them together. So I'm basically going to say if the input is such that it corresponds to row 0, which is first row, ANDed with the input is such that it corresponds to row number 2 and 3, and kind of all the, we go through all the rows which have, with all the rows that have an output of 0. So let's look at why it logically works out. So very first row has an output of 0, and it corresponds to 0, 0, 0, 0, which, if you recall, in Maxterm terms means A1 or A0 or B1 or B0. Okay, so this particular Maxterm, A1 or A0 or B1 or B0, takes, under what condition is it 0? When does this expression A1 or A0 or B1 or B0 takes on the value 0? Well, that is the case when all 4 are 0. Right? Because if any one of them, if A1 or A0 or B1 or B0, if any one of them is 1, then this expression A1, A0, A1 or A0 or B1 or B0 will have the value 1. So this Maxterm takes on the value 0 if input is 0, 0, 0, 0. Likewise, the next Maxterm, A1 or A0 or B1 or not B0, it takes the value 0 when when A1 is 0, A0 is 0, B1 is 0, and B0 is 1, which corresponds to the second row. And so forth. So this expression that I have written out here, where I'm saying that Maxterm 0 and maxterm 1 and maxterm 2 and maxterm 3 and so on and so forth. So see, these 0, 1, 2, 3, 4, 5, 6, 7, 10, 11, they correspond to the rows where the output is taking 0. So if you think about logically, what I'm saying is that maxterm 0 takes on the value 0. So take the, now think about what happens to this overall expression. So I'm doing an ANDing out here. This expression will take on the value 1 when each one of these max term has the value 1, right? Because at the top level, I'm doing an ANDing. So this overall expression is a bunch of ANDing. And any expression which is a bunch of AND, for it to be true, each one of the constituent terms has to be true. So what this is saying is that maxterm 0 has to take the value 1, and maxterm 1 has to take the value 1, and maxterm 2 has to take the value 1, and so on and so forth. Now, when do you think that would be the case? What value should the input take so that M0 is 1, and M1 is 1, and M2 is 1, and M3 is 1, and so on and so forth? Let's start with M0. If I say M0, maxterm 0 is 1, that is, the input is such that maxterm 0 evaluates to 1, what does that mean?
One of them is not 0.
Right. So what can you say in terms of truth table? Which row am I in or not in?
All the other rows
Except 0, right? So M0 being 1 means all the rows other than row 0. And M1. So M1 would mean all the rows other than 1. So now M0 and M1 means all the rows other than 0 and 1. M2 means all the rows other than 2. M3 being 1 means all the rows other than 3, and so on and so forth. So this whole expression says all the rows other than 0, 1, 2, 3, 4, 5, 6, 7, 10, and 11, which corresponds to the remaining rows, which are rows 8, 9, 12, 13, 14, 15. Right? So with the max term, we are basically listing the rows where the function does not take the value 1. That's basically what is happening. So I'm excluding the rows. So again, max term being 1 is excluding one of the rows. So M0 is excluding row 0, M1 is excluding row 1, M6 is excluding row 6. And when I take the ANDing of it, I'm excluding rows 0, 1, 2, 3, 4, 5, 6, 7, 10, 11. So the remaining rows are allowable. That is, if the input corresponds to any one of the remaining rows, only then the function would be 1, otherwise the function would be 0, which is exactly what we want. So in terms of like a cookie cutter recipe, essentially what all of this boils down to is that for minterm, you focus on rows where the function is taking the value 1, and then you OR those minterms together. Whereas to write the same function in the maxterm form, you look at the rows which correspond to output 0, and then you AND those max terms together. Okay, but that's the recipe. You should really kind of have a feeling of what is going on under the hood. Much more common is the minterm way of looking things, but max term is rarer, but oftentimes max term is useful. You might imagine, like looking at this particular function, you can see that the max term way leads to a lot more max terms, whereas the minterm approach had fewer minterms. So depending upon whether the function has more ones in the output rows or more zeros, one or the other may be more compact. So let's try an example. So I have this function. So first thing it asks for it. What the problem asks is, what is the dual of this function? So anyone help me out? So I want to write the dual of this function. So what happened? Okay, so Help me out. Anyone remembers dual? Okay, so louder. X or not Y. Good. Remember, it was replace and by or by and, zeros by one, ones by zeros. Everything else remains unchanged. So that's the dual. And then it says write it meaning the dual function, in the normal form. So we want to write it in a. So firstly, is this this particular form? So if I'm looking at this function f dx comma y, what kind of is the expression on the right, is it one of the normal forms? If so, which one? Yeah, so it's a conjunctive normal form because each one of these is a max term, and therefore it's a conjunctive normal form. So I have two max terms, and they this one, and I'm ANDing them together. So it's the conjunctive normal form, or CNF. What if I want DNF? So one way to do the DNF is that I expand it out using the Boolean logic things that we have learned before. So we basically make use of distributivity. So we can write this thing as this is equal to x or not x or y. Let's see. No, messing it up. X and not x or y, or not y and not x or y. And then you further simplify it. So now at the top level I have an or, and then you further expand it. I'm not going to walk through it. I would like you to do it on your own, but at the end you are going to end up with a bunch of ors, bunch of and expressions which are ored together. So that would be your midterm way of looking at it. That's one approach. The other is I basically make a truth table. So let's do the truth table approach. So I have x, y. They can take four values: 0, 0, 0, 1, 1, 0, 1, 1. I look at the output. So it's, if it is 0, 0, so x is 0. So the first term becomes 0. Sorry, x or not y. So 0, 0 means the first term is 1. And the second term is also 1. And therefore output is 1 and 1, which is 1. Next term, x is 0. So 0 or 0. So the first term is 0. So 0 and nothing matters. So this is going to be 0. And likewise, this one is going to be 0. And the fourth term is going to be a 1. So this is going to be a truth table. Now, can someone tell me the CNF of this? So the strategy, if it's CNF, was which rows do we focus on? Rows with 1. So row number, first row and the last row. And the minterms corresponding to them are not x and not y, or x and y. So yeah, so you can always go with the truth table, or you can kind of keep doing the algebraic way, which sort of I'm not doing. Okay, let's look at another. Okay, let's see. Do I have another example? Let's consider this function also. So this is FABC. Is it in normal form? Why not? They are not minterms. Okay. And the reason they are not minterm is that we look at A and B is missing the C, and likewise B and C is missing the A and C is missing. Anyone recall what function is this? Okay, now you stop answering. Someone else has to help me. Okay, so majority function. Okay, so help me with creating a CNF for this. How would you go around?
do it with or without a truth table?
Whichever. So suggest one approach. We'll discuss others. Okay. Oh, huh?
We can do a truth table.
Okay, so you're going to do a truth table, right? So I have 3 inputs, truth table with 8 rows. Do it out. Yeah.
Because they're all the same operation between these parentheses, you could just add the C in the parentheses without changing the total output of the parentheses.
You could, yeah. So that would be another approach, or yet another approach, a general approach for looking for something like this is the following. If I have A and B, okay, so A and B is another way of saying is C doesn't matter, right? So which is equivalent to saying A and B and C, or A and B and not C, right? So C doesn't matter, one of them is true. And I can do the same thing with each one of the expression. So I can literally expand. I mean, this is already in the sum of product form. So I can just take each one of them and kind of expand it in this particular way. So, and then you'll see you'll end up with some redundant, some duplicate minterms, and can kind of remove them out. So I can play the same game with B and C. So that expands to A and B and C, or not A and B and C, and the same thing with A and C, and then kind of do it. So that would be kind of an algebraic way of approaching the problem.
So then we would have like some set of well, okay. So for the first 2 terms, there would be adjacent minterms because you're changing the last.
Right.
But for the next one,
they will not be adjacent.
Yeah,
they will be rows which are far apart in the truth table. Yeah. So actually, if you look at the, so you're making an interesting point, which will come later. So B and C really is basically pointing out 2 rows, right? It's pointing out the row corresponding to A and B and C, and also the row corresponding to not A and B and C, right? So because, or another way of saying is, we don't care about the value of A. Okay, it can take either one. We'll revisit this thing. So given a function, you can have a truth table, map it to CNF, map it to DNF, multiple different ways you can kind of go around doing this thing. But ultimately, these minterms, maxterm are just the mathematical side of things. In a circuit implementation, you have to map them to gates. But if you look at this CNF and DNF, we are almost there. I mean, they correspond to gates, right? I mean, we have AND gates, some inverters, and some OR gates. So in case of CNF, we have OR gates, and then they're ANDed together. So I have a bunch of OR gates in level 1, and the outputs of those OR gates feeds into a gigantic AND gate. In case of DNF, sum of products, I have a bunch of AND gates, and their output feeds to an OR gate. So primitive gates, as you can see, once we have things in DNF and CNF, all I need are AND gates, OR gates, and NOTs, and I can implement any function, right? So given any mathematical function can be written as a truth table. Any truth table can be mapped to a CNF or DNF. And once we have an expression in terms of CNF or DNF, then all I need are AND gate, OR gate, and NOT gate. And moreover, we saw previous lecture that because of De Morgan's law, if I have an and NOT, I can create OR, and vice versa. So once I give you an infinite supply of AND gate and NOT gate, or even better, if I just give you an infinite supply of NAND gates, or just an infinite supply of NOR gates, then you can implement any mathematical function that is possible. Okay, I mean, essentially anything that can be computed can be implemented just with an infinite supply of 2 input NAND gates or 2 input NOR gates, or AND plus NOT, or OR plus NOT, any combination of these. And that's a pretty interesting thing. I mean, just from these primitive gates, you can implement any mathematical function that there is, okay, or anything that can be computed can be done. Now, of course, you don't necessarily implement things that way because it would be very inefficient, generally speaking. But at a high level idea remains that I come up with a Boolean logic expression and then map it to gates. And DNF and CNF are just specific forms of Boolean expression for given a function, and then we kind of map to it. Now, so already we saw that for a given mathematical function, I can have two forms of expression, DNF and CNF, and in general more. Like in this particular case, this is neither DNF nor CNF. It's yet another expression. So clearly, a mathematical function can be implemented in many different, can be expressed in many different ways, and each one of them can be mapped to gates. So in this particular case, you would see that the gate level implementation is going to look like I will have an AND gate with A and B. So that corresponds to the first term. I'll have another AND gate which would have B and C. And I'll have another AND gate which is going to have A and C. And I'm going to take their output and feed them into an OR gate. And this is going to be my output. Okay, so this is literally just looking at this expression and writing this out. Question then becomes, which implementation is better? How can I compare for a given function? If I give you two expressions, they will map to two different ways to the gates. How do we say one is better than the other? So there are many different ways you can kind of look at it. One way we can say is how much cost, how many whatever dollars would it cost, okay, or whatever. In this case, it would be some tiny fraction of a dollar, but how much money? How much silicon area would it take if I'm doing a implementation as a electronic gate? How fast would it be? If I change A, how many picoseconds later does output change? How much power would it take if I'm using it in my system? All these are valid metrics of looking at things. The one which we would usually consider, at least initially in the class, is the one where we say how much area, how much silicon would it take? And the way it is done is the following, that we basically say to the first order, the cost of a gate is proportional to the number of inputs it has. Okay, so for example, if I have a 2-input or AND gate versus a 3-input AND gate, then the 3-input AND gate is 50% costlier than the 2-input AND gate, and so on and so forth. So this is just a good rule of thumb, which is which has some physical validity. It's not perfect, but it's kind of a reasonable thing to do. So oftentimes in the problems, I will say, assume the cost of gates is so much, and now come up with a low cost implementation. Okay, so the idea is then you're going to come up with a Boolean implementation and then map it to gates and then evaluate the cost. Okay. So if I want to map this guy, this is an expression we already saw. So in this particular case, let's see, do I already have the solution to this? Yeah. So if I were to implement this, so I need a AND gate where I feed X, and I need a NOT to feed Y. So that is this term. And I need another AND gate to which I feed the NOT X, and I have a Y, and I combine these two together into an OR gate and feed it to the output. So once you have the expression, kind of mapping it to the gates is relatively straightforward. Now let's do a further thing. Let's say I do not give you OR gate and AND gate. Let's say I only give you NAND gates. So and now I want to kind of implement this thing. So this is where De Morgan laws kind of help us out. So if you recall, and I'm going to flip back to, well, maybe I'll just what does this correspond to in according to De Morgan's law? Not x and y, right? Okay. So now let's imagine I look at this wire which is going from the output of the AND gate to the input of the OR gate. And I can replace, on this wire I can put two NOT gates back to back, right? That doesn't change anything. So let's say I place an inverter at the output of this AND gate, and I place an inverter at the input of this OR gate. And I'm representing the inverter just by this bubble. And likewise, I play the same game out here. I place an inverter at the output of this AND gate and an inverter at the other input of this OR gate. And now if I focus on this guy, using this De Morgan, I can replace it by this, right? So I started out with this OR of AND, but now I have NAND in both stages, right? So so a wire, I put two back-to-back inverter on the wire, one at the output of this gate, one at the input of the other gate, and then I applied De Morgan, and I ended up with two stages of NAND gate. Okay, so anytime I have a sum of product, that means including a DNF representation, then I can implement it using NAND gates alone. And likewise, I'll let you kind of ponder over it. If I give you an expression which is product of sums, that is, it is a CNF, then I can implement it using NOR gates alone. Okay, just again by applying the De Morgan's law. So that is kind of a informal hand-wavy proof of saying that NAND gates are enough, right? I mean, if I just give you a large supply of NAND gates, you can implement anything. And if I give you a large supply of NOR gates, again, also can question.
So we get to use NOR gates and NOT.
NOT can be constructed using a NOR gate also, right? I mean, if I give you a two-input NOR gate, you just tie its inputs together, that's a NOT gate, right? Any questions on this one? So another way of saying is NAND gates are universal. I can implement any mathematical function using that. Likewise, NOR gates are universal. I can implement any mathematical function using that.
From an implementation cost, what generally turns out to be cheaper, NAND or NOR?
Depends on the technology. Yeah. So there's no one answer. If any of you have already, I don't know, if you have done any semiconductor type courses where technologies where they call P-well, N-well, depending upon what kind of semiconductor technology is, for the same speed and the same power, either the NAND is faster, NAND is smaller, or the NOR is smaller. So it depends on which kind of technology it is. More commonly, NAND is smaller, but it doesn't have to be that way. And of course, this is just about electronic technologies. If you're looking into biological or molecular type implementation, some of these things which are coming into play, it could be different also. One other point I would like to make is that the fact that we use NAND or NOR as our universal gates is peculiar because we are using, in an EECS department, we usually deal with electronic implementations currently. It's certainly possible that there are some other gate structures that exist which are also universal, okay? And maybe in the homework, I'll let you think about some of those. So a universal gate is one which basically we define as that if I give you an infinite supply of that, then you can implement any mathematical function. Or a set of gates become universal if just using that set of gates, you can implement any mathematical function. So NAND and NOR are just not by themselves unique. Likewise, there are some gates which are not, like XOR gate, which sort of you saw in your design assignment 1. It is not universal. You cannot implement every mathematical function using that. So even though it's a complicated gate. Okay, so these are other primitive gates. So let's move on to the next one. So we saw now how we can take a mathematical function, we can map it to gates through kind of at least some semblance of a systematic process. Let's look at how we can kind of optimize these things more. So what we are going to look at is in this module is how do we design combinational logic such that it is optimized. And the thing to bear in mind is that in industrial practice, you are probably never ever, I mean, after this course is, or maybe after your UCLA undergrad studies, you'll probably never have to design these things by hand. I mean, there are essentially, just like you have compilers for software, you have compilers for hardware. You write things in a either draw it the way you in Logisim, or you write it in a programming language, and then the output is hardware. Output is the mapping in terms of gates. So that's how kind of things happen, because in this course you're dealing with maybe at most tens of gates or maybe hundreds, whereas industrial stuff goes into millions, and also you're not going to do it by hand. So the stuff that we are talking about in this thing, one way of thinking about it, this is what those compilers do under the hood. Okay, and so that's probably a better way of thinking about it. That the techniques we are talking about are things that go under the hood, and it's not something that you would manually apply. Okay, so let's walk through how this process kind of works out. So let's consider now, so we have looked at the thermostat function a lot, so we're going to have a change of function. So we are going to look at the function prime or 1. Okay, so this is a function which takes 4 single bit input DCBA. It thinks of this number DCBA as a binary number, and it says that the output is 1 if that 4-bit number is either 1 or is a prime number. So let me expand upon that. So again, DCBA corresponds to an integer. So again, let me, does anyone not know binary arithmetic? Okay, I don't see any. You don't? No, everyone. Okay, so I'm going to skip the next few slides with the assumption that everyone knows that. Okay, so DCBA, there are 0 through 15 possible values. So now we are thinking of thinking these 4-bit patterns as 4-bit positive binary numbers. And so let me skip through. So the first row is row number 0, and we have defined that the output of this function should be 1 when the input is either 1 or a prime number. So row number 0, output is 0. Row number 1, output is 1. Row number 2 is a prime number, so output is going to be 1, and so on and so forth. So row number 1, 2, 3, 5, 7, 11, and 13 are the ones which where it takes on the output is going to be 1, the others are going to be 0. Incidentally, a lot of places this function is referred to simply as a prime function, which is obviously incorrect. 1 is not a prime number, but I think that's a mistake very commonly made by many. So if it simply said a prime number, then the row corresponding to 1 has to be 0. Okay, so I have this function now, and now we have the truth table corresponding to 1 or prime. So one approach we can do it is by starting out with our DNF and CNF kind of approach, which we saw in the previous module. So I'm going to skip through this thing, so a bunch of steps, because we just went through it earlier in the lecture. So if I'm implementing it as a disjunctive normal form, then what do you think the expression will look like? So Minterm based approach. So you have the truth table. What would be the expression in terms of Minterms? Go ahead. No. Just give me in terms of Minterms. Yeah. So sigma m 1, 2, 3, 5, 7, 11, 13. Right. That's what it boils down to. Okay. If I were to ask you to do it in a CNF form, which is the Maxterms form, it would be looking at the zeros, right? So product of Maxterms number 0, 4, 6, 8, 9, 10, 12, 14, 15, right? Okay. So we just saw that. So that's basically the next few slides are describing. That's all that is happening out here. Okay, so it's just literally listing. This is the Mintem form we are doing. So we are listing all the rows which correspond to 1. We write down the expressions each laboriously, but the end result is we come up with this. Okay, so so we do this thing. The problem with this is that if you look at the underlying expression, it is pretty big and messy, and it kind of just give me a sec. So it kind of begs the question: is it the best we can do? I mean, if I'm using this, I need 1, 2, 3, 4, 5, 6, 7. I need 7 AND gates with 4 inputs each. And I need an OR gate with 1, 2, 3, 4, 5, 6, 7 inputs, right? So this implementation is going to need implementing this thing is going to need 7 AND gates of 4 inputs plus 1 OR gate of 7 inputs. And question which comes up, can I do it better? And that's what sort of we are going to do. Yeah, go ahead now.
Well, I mean, we could look at the lowest order bit and then short it out if we know.
Yeah, you're jumping the gun, so just bear with me. So yeah, you can. So basic idea is a little bit like what we do in regular algebra. We are going to merge these things, right? So remember, previously we saw that if I had the expression of the type A and B and I was missing C, so I was expanding it to A and B and C or A and B and not C. I can go the other way around. So let's see if something like this is happening out here. Let's look at these two terms. Okay, if I look at these two terms, if you see that they only differ in A, so I can absorb the A. That's the absorption, right? So I can just look at these two locally, and their ORing is going to be the same as not D and not C and B. A disappears, and I can play the same game repeatedly to come up with a more compact expression. And what we're going to see is how to do it systematically, how to do it so that we indeed end up with a low-cost implementation. Okay, so this was the underlying implementation. You can see kind of pretty messy. Okay, lots of gates, but there is a certain beauty to it. It's a very regular structure. In fact, if you, I mean, it's still the case that oftentimes there are these programmable silicon chips, and what they do is they give you a structure like this where there is an OR gate and a bunch of AND gates, and the AND gates are feeding into the OR gates, and then they let you decide whether what inputs you are connecting to them. So the idea is you give the structure, and then by blowing some fuses or programming some switches, you can literally take any input and feed them into any of these AND gates, and then make your chip do an arbitrary mathematical function. So they are so-called programmable chips, where in software you tie inputs to your inputs to your system, like A, B, C, D in this case, to select inputs to these AND gates and then implement arbitrary mathematical functions. So they are very useful because I can just buy these programmable chips and kind of configure them in my system using software. So they're nice, but let's see if I can go with if I can try to do what sort of was being suggested, optimize these things. Okay, so the key idea out here is, which is, let's put some of these minterms be combined. Could I take one, two or more minterms and then reduce them into a single term? Okay, so that I end up with a smaller representation. So this is our 1 or prime thing, except that what I've done is I've only listed the rows where the output is 1, and for other rows I've said otherwise the output is 0. Okay. So if I look at these two rows, row number 2 and row number 3, DCBA takes a value 0010 out here and 0011 out here. and kind of like what I suggested, they differ only in one place. They only differ in the A position. So another way of writing this thing would be to say that all I want is D, C, and B to be 0, 0, and 1, and I don't care about A. In Boolean logic term, that means is that I take these two minterms, I look at their ORing, and then A disappears because A is taking both possible values. So this expression, minterm number 2 or minterm number 3, reduces to the expression not D and not C and B, and A disappears. So what happens now? As a result of this, instead of 2 4-input AND gates, I have 1 3-input AND gate, and the OR gate, I don't need to OR these things together. So there's obviously some savings happening out here. And I can play this game again and again. So firstly, whenever we do this kind of combination of minterms, so what's happening is I started out with two minterms, 0010 and 0011. But we see that 0 and they differ only one place, namely A. So we basically say that I can combine them and I can represent the merged thing as 001x, which is another way of saying is D should be 0, C should be 0, B should be 1, and A, I do not care. A could be either 0, A can be 0 or 1. Both of them are acceptable. So X means bit can be either 0 or 1. And this type of an expression, 001x, where x stands for both 0 and 1, is called an implicant of the function. Okay, so previously, 0010 was a minterm, 0011 was a minterm, but 001x is called an implicant because it depends upon 3 of the inputs, and the 4th input is absent now because either of its 2 values are acceptable. So the term implicant comes from the fact that it implies the function is true. That is, whenever 001x is true, then the function is true. Okay, that's why it's called the implicant. So 001x is equivalent to saying not D and not C and B, and so it's basically saying whenever not D and not C and B is true, then my function is true. Therefore, this is an implicant. Do you think a minterm is an implicant? Does the minterm corresponding to a row where the output is 1, is that an implicant? So let's look at not D and not C and B and not A. Is that an implicant? It is, because whenever this particular expression is 1, then our particular function is 1 in its output. So a minterm is a specific case, a minterm corresponding to a row where my function takes an output 1 is also an implicant. So a general minterm, so my 4-input function has 16 possible minterms. So if I pick an arbitrary minterm, it may or may not be an implicant, but a minterm of that function, which basically means minterm of the where the function is taking the value 1, that is an implicant. And likewise, an implicant may or may not be a function. May or may not be a minterm. What other minterms can be combined? So if you look at this, do you see other things that can be combined together? So let's focus on firstly pairwise combination. Are there other neighboring things at the back? Which one? 5th and 7th can be combined because they differ in the position B. Any other? 1 and 5 can be combined. Yes, they differ. And likewise, you can kind of question then becomes like, instead of manually looking at like this, is there a cleaner way of doing it? Is there a cleaner mathematical way of identifying this neighboring relationship, right? I mean, saying that are two things neighboring. So there are many ways of approaching this problem. The approach that I'm using, which is the same one in the textbook, is the one which is used by the design tools quite a bit. Okay, so oftentimes you would see, in fact, the previous lecture is also the other version of the one taught by Professor Potkanak, and you see that he drew these things. We're going to come to these shortly. These are called Karnaugh maps or K maps. We are going to come to it in the latter part of this module, but I first want to introduce how things are actually done by these software tools, because that's the real sort of way it is approached. So the idea is that I have a function with a bunch of inputs, A, B, C, D in our case, or let's say ABC. I'm just going to look at 3. Each one of these inputs can be viewed as a dimension in an n-dimensional space where I have n inputs to my function. So if I'm looking at a function with ABC, then I have a 3-dimensional space. One axis corresponds to A, one axis corresponds to B, one axis corresponds to C. And we are dealing with a binary world, so along each axis, I have only 2 possible values, 0 or 1. So in our particular case, I have a 3-dimensional function A, B, C, and A can take value 0 or 1, B can take value 0 or 1, C can take value 0 or 1. And so you can think of the structure as a cube. And the corners of the cubes correspond to the coordinates. So I have an origin here, 0, 0, 0. On the right hand side, I have 0, 0, 1. So out here, 0, 1, 1, 1, 1, 1, and so 8 possible 8 corners of this cube. What do you think the corners represent?
Each possible include.
No, inputs are the dimensions, right? A, B, C. Or each possible input pattern. So 1, 1, 1 is a specific input value. Yeah. Okay. So, but do they represent something else? They are the minterms or the maxterms. Okay. So let's for now just think in terms of midterms. So they represent our minterms. But you're right, minterms or maxterms. We can represent them either way. So they represent the minterms, right? So 1, 1, 1 corresponds to the minterm A, B, C, or which according to you, when the input took the value A equal to 1, B equal to 1, C equal to 1. Okay. So now any given, so this is my underlying kind of n-dimensional structure. Any given function corresponds to, so I can talk about for any given function where it takes the value 1. So for example, let's say I have this function f equal to m sum of the minterms 1, 2, 3, 5, 7. So this is again my 1 or prime function. So I can write this thing by saying that this function has the value 1 at those corners where I have this cyan color bubble sitting. Okay, so it's basically saying this function is a sum of minterms 1, 2, 3, 5, 7, and therefore I put those 1, 2, 3, 5, 7. So 1 is the 0, 0, 1. 0, 1, 1 is the minterm number 3, 0, 1, 0 is minterm number 2, 1, 0, 1 is minterm number 5, 1, 1, 1 is minterm number 7. Okay. Now looking at this, and if we say 2 minterms differ in only 1 position, what does it mean geometrically? They are adjacent, they have an edge between them, right? So 1, 0, 1 and 1, 1, 1, they differ only in the B dimension. So they have an edge going, so 1, 0, 1, so B is 0, 1, 1, 1, B is 1, and so they are connected by an edge. Okay. Likewise, 1, 1, 1 and 0, 1, 1 are neighboring because they differ in C. Okay. And likewise 0, 1, 0, 1, 0, which is back out here, and 0, 1, 1, they are adjacent, they're connected by an edge, and they differ in A, and so on and so forth. So previously this merging stuff that we were talking about, in this case now it boils down to whether there is an edge between these 2 nodes or not. So you can imagine now the underlying software tool, what it does is when it reads these functions and all, it represents a function by these n-dimensional cubes, okay, and then some of the vertices of the cube are marked because that is where the function is 1, and then it starts looking at which one of the edges of that n-dimensional cube are connecting corners which are taking value 1. So it kind of systematically goes through that process. Looking at this, another thing kind of appears. So let's look at this right-hand side plane, which corresponds to 101, 111, 011, and 001. If you look at it, you would see in this case that A is equal to 1, but B and C are taking on all the 4 possible values, 0, 0, 1, 0, 1, 1, and 0, 1, right? So this plane with, on the right hand side, let me just do it on the laptop so that makes it to the video. So this plane that we have on the right hand side, this corresponds to taking on the value, so this whole plane corresponds to A equal to 1, and B and C are taking all the 4 possible values. So I can I can actually extend my merging concept beyond edges to planes, right? I can take these 4 minterms and I can combine all of them and simply say this is A, XXA, okay? Because B and C I don't care about, they are allowed to take both 0 and 1, and all 4 possible combinations result in a function taking the value 1. So by going into this cube view of things, or this hypercube way of looking at things, I can merge edges, I can merge planes, I can merge 3D cubes, I can merge 4D cubes, or if I have a 100 input function, then I can merge 99 dimensional hypercubes to form more compact stuff. And I mean, as human beings, we'll never do that large number of dimensions, but for a program, it's easy to kind of manipulate these kind of things. So the problem then becomes, how do I merge? There might be many different ways of merging stuff out here, right? I mean, we clearly see that there are 5 edges where merging can take place, and there is a plane where merging can take place. And there are many different ways I could go around merging, sort of corners and minterms like this. And the question then becomes is which strategy is the best? Now the problem out here is that these kind of problems are the so-called NP-complete problems, which basically means in theoretic terms that we do not know of an efficient way of solving these things other than either trying heuristics or essentially you do an exhaustive search, okay? So there are no known efficient, scalable ways of solving these, but that doesn't prevent us from solving these. I mean, you come up with approaches that work most of the time, good enough, and certainly better than kind of what humans might do. So let's walk through this example more. So we merge minterms into edges and planes and even higher dimensional things. So for example, I can merge this pink color edge, and this edge will be 1x1 because it is connecting 101 with 111. So x corresponds to B, which can take either value. I can also do a merging on this second edge that corresponds to x11 because C is allowed to change. Or this bottom edge, which is 0x1, this edge at the front, which is x01, and then finally this edge which is at the back, which is 01x, and we can merge edges into faces. So if I have a face where all the 4 edges are marked, then I can combine these, and that is xx1. Now, at the end of it, the goal is the following, that we started out by saying that my function is an ORing of a bunch of vertices corresponding to the minterms. But then we started coalescing these minterms into edges and faces, and in higher dimension could be cubes and 4D cubes and so on and so forth. And the goal that we are looking for is there a way I can express my function as a ORing of these higher dimensional objects, planes and edges and all, because we know that a plane is cheaper to implement. This plane is xx1, which is a single bit input. So it's cheaper than 4 minterms. Or an edge like 0x1 is cheaper than 2 separate minterms. So higher dimensional things are cheaper. face is cheaper than edge is cheaper than a vertex. So the goal out here is what is the minimal number of faces, edges, vertices I can pick which are cheap, and which together take care of all the minterms which I had originally marked. So looking at this, so going with the intuition that face is cheaper than edge is cheaper than a corner, and I want to cover every corner which was cyan colored. So looking at this, you can say, a good strategy is I take this face, so in one go I take care of 4 of the corners which were marked, and then I take care of, and I use this edge 0, 1x, which takes care of this remaining thing. It's cheaper than using 0, 1, 0, the standalone minterm, because I can do 0, 1x. This corner 0, 1, 1 is present both in the plane and in the edge, but that is fine. I'm just covering it twice. So my problem of designing an efficient circuit boils down to covering all the vertices as efficiently as possible, where efficiently is defined by faces are cheaper than edges are cheaper than corners, and at the end of it, I need to cover all the corners which were originally there, all the minterms which were originally there. So that intuition, like I said, in this case says go with the plane, which is xx1, go with this back edge 0, 1x, and that is what we see as the function out here. My animation was messed up because we had it all along at the bottom, but it's basically f is equal to xx1 or 0, 1x. xx1 is the plane, 0, 1x is the back, is the edge which we have at the back. And together, these two are covering all the 5 cyan colored vertices, which were my minterms 1, 2, 3, 5, 7. So that's kind of the intuitive strategy. So you mark these things and then coalesce stuff into as high dimensional stuff as you can. So plane, then edges, then vertices, and then write your function in terms of these things. So now I end up with this A or not C and B. Whereas my original expression, jumping back several slides, at least for the 4-input case, was sort of tremendously complicated, and even for the 3-input case, we have five possible minterms. So it was a complicated beast. So that's kind of the strategy out here. Now, of course, the problem with this is that if you are going to have, let's say I give you a 4-dimensional function, firstly, I don't know how you can even begin to draw this thing. I'm going to show an attempt at drawing that. And beyond that, it would be horrendously hard to even attempt. Okay, of course, for a software to manipulate this thing is not hard, but for as humans, we kind of, the nice thing out here is a geometric interpretation, but if you cannot visualize it, if you cannot draw it, it's going to be pretty hard to kind of do it. So there are alternative ways we can kind of do it, but let's take a shot at expressing a 4-dimensional function. So this is the 4-dimensional function. Okay, so what is happening is, so it's a little bit tricky to kind of, let's see, how are we doing time-wise? Yeah, we have plenty of time. Okay, so this is our 4-dimensional prime, M1, 2, 3, 5, 7, 11, 13. And now what is happening is the 4th dimension, which is our D dimension, corresponds to, so if you can make it out or not, there are 2 cubes out here. There is an interior cube, which is sort of, follow my cursor, so which is, there is an interior smaller cube, which is sitting out here. And then surrounding it is a larger cube. And the 2 are connected in that 4th dimension, which is the D dimension out here. So the inner cube corresponds to D equal to 0, and the outer cube corresponds to D equal to 1. And then these edges that you see, which are going from the corners of the outer cube to the corners of the inner cube, are the one where D is changing from 1 to 0, 0 to 1. Okay. So in this representation, I have 16 possible corners, which correspond to 16 minterms, and my specific function, the 1 or prime function, takes on the value 1 at minterms 1, 2, 3, 5, 7, 11, 13. So that's 3 plus 4, 7 possible minterms. And they correspond to 0, 0, 0, 1. So if you see out here, 0, 0, 0, 1 is marked in black, bold. 0, 0, next one is 0, 0, 1, 0. So which is this guy out here, 0, 0, 1, 0. 0, 0, 1, 1 is out here. And this is 5, the 7 is out here, this is 11, this is 11, this is 13, and then yeah, so there's 13, 7, yeah, okay, so that's covering all of them. And we play kind of the same game out here, that we can mark things that can be merged. So edges that correspond to edges that are connecting to minterms of this function, they are marked in bold. So like 0, 0, 1, 0 and 0, 0, 1, 1 is marked in bold because it differs only in A. Likewise, 0, 0, 1, 1 and 1, 0, 1, 1, it differs only in D, and therefore it is marked. And likewise, I have a plane out here, which kind of merges all of these. So looking at this, let's play some geometry. So what do you think would be a good way of covering this function? So let's start by marking these edges in terms of our notation. So let's look at this edge. In terms of our implicant notation, what is the representation of that? So it's connecting 0, 1, 0, 1 to 1, 1, 0, 1. So how would you write it? X1, 0, 1. What about this guy at the back? 0, 0, 1, X. Good. What about this guy? X, 0, 1, 1. And then in here we have a plane, so we're not going to worry about the edges because we know we already have a plane. So what do you think the plane is? 0, x, x1. Good. So D is 0, B and C can take any value, A is 1. 0, x, x1. Okay. And now staring at this, what do you think would be a good way of implementing this function? So I guess sort of I take the plane and I take all the 3 edges we marked, right? We need all 3 of them, right? Because again, remember, edges are better than minterms, so it's better to have a corner covered twice if necessary. So in this particular case, my good way of implementing the function becomes 0, x, x1 or x1, 0, 1 or 0, 0, 1, x or x0, 1, 1. Okay. So that's kind of the process that we have to follow, and I think that's what we have really out here. A and not D corresponds to our plane, and the other 3 correspond to the 3 edges. Question?
Is that optimal?
For this particular example, it is. Okay, because it's such a simple example. The problem though is that for large problems, we do not, like I was saying, these are NP complete, actually NP hard problem. So we do not know, I guess the real answer is we do not even know whether an efficient process exists. Okay, this is a so-called P equal to NP problem. Some of you may have heard or not heard about it, but yeah. Let me take your question first.
So you have, in this example, your midterm has 7 terms.
I had 7 minterms.
If in another example your midterm had 9 midterms, would a max term solution be faster?
Max term solution would be, unfortunately, it's not easy to say whether it is. You cannot unambiguously say that it would, because remember, now that we are merging stuff, so it partly depends how these things are distributed in my 4D space, and so how mergeable they are. So it may be that I may start out with more minterms, fewer max term, but by merging, I may end up with a more efficient solution with the minterm approach. Yeah, so it's not easy to answer, unfortunately.
And then would it
yes, more complicated strategies can, but it's not so much looking at minterm and maxterm, but we start going where, right, remember right now we are doing like sum of product, product of sum, but you can imagine doing multiple levels of things. So I may have one level which is sum of product, then a next level which takes bunch of sum of products, puts them into a product of sum. So there are multi-level design strategies, and generally they are what are used. As humans, it's very hard for us to do it, but cat design tools do it. Okay, let me go in order. So you had a question first and back.
So like basically the ease with which we can reduce the problem depends on the adjacency, right? Like,
it depends on the adjacency. It depends on the structure of your function.
okay, so if you have a lot of corners that are distributed all over the place and they don't share rows and columns,
then you're stuck. So in fact, you can imagine these kind of really weirdo functions where like there are lots of things, but I just cannot sort of merge them, right? So they're kind of always just. I mean, even in this example, you can kind of try to construct these things. So there are these hard functions which cannot be handled. I mean, then they're your worst case situations. Yeah. Okay. Yeah.
Is there a convention by which each of the edges are named, or do you kind of arbitrarily put zeros and ones in each?
Well, they're following the dimension, right? So I guess the convention we were using was D goes first, then C, then B, then A. I guess. Yeah, I mean, I should state it that what it is saying. So I guess I was implying out here that when I'm writing this thing, it's DCBA, but it's good to state that explicitly. Yeah, yeah. So there's no convention; you have to state it. Yeah.
So I guess similar to his question, like, how did you get the direction of the arrows for CBDA?
Oh, they are going from 0 to 1.
And like, was that placement arbitrary or?
I guess I'm following that for horizontal axis, 0 is left, 1 is right. For going top to bottom, higher is 1, lower is 0. In to out, in is 0, out is 1.
Would changing that ever make a difference?
No, it's just a convention. So I guess the way I'm drawing, at least A, B, and C, the way I'm drawing is the more conventional way of drawing three-dimensional stuff. For D, I mean, there is no convention, so we kind of. By the way, I mean, since obviously I'm not drawing these figures by hand myself, so my convention in part is dictated by the book because the book already gave me the figures. Okay, but again, to sort of answer your question seriously, there's no convention. Any other question on this? So to summarize kind of this thing out here, if I have a function with n inputs, I will be dealing with an n-dimensional binary space. I'll be dealing with an n-dimensional cube whose 2 to the power n corners are going to be, some of them are going to be colored corresponding to the minterms where the function takes the value 1. I'm going to merging these things. I'm going to be merging them into edges, planes, cubes, 4-dimensional cubes, 5-dimensional cubes, whatever, as many dimensions as I have. And then I have to find a good way of selecting some of these merged entities to cover all my original colored corners, right? That's the algorithm problem that we have.
So in a 4-dimensional, in this representation, is there kind of like a neat mix simplification where you can take 3 out of the 4 dimensions and combine them? Like, you know what I mean? Like, if you have like a greater one, would you do that?
Yeah. So these are kind of what are called as heuristic strategies that the computer programs do use. So they try to identify, is there a dimension which I can eliminate first? Okay. So they begin to apply some sort of, it's a little bit like algebraic simplification that we do. So we identify which variable to factor out first and then the next one. And also they do make use of these. It's a topic in itself. There is, I guess, there are a couple of courses at UCLA which do go into some of these issues, but the time in which these things were really hot was like 90s, and I guess at this stage the design tools and all are pretty efficient, and also between late 70s and mid 90s a lot of work happened. There is those of you who are in CS theory and all, there is basically you will probably see in your theory courses and all, there is a representation for these things, something called BDDs, binary decision diagrams, as they are called. So they're very efficient data structure which represent these kind of things. And then the problem, this problem of what's called a covering problem, and it's also there's something called a satisfiability problem. So there are a lot of work going on because equivalent problems occur in many other domains, not just circuit design. So there's a lot of effort which has gone into creating very optimized heuristics and all, which work very well, and that's what they get used. And there are a couple of companies, probably the most famous company in this space is a company called Synopsys, and its tools are used very widely. So they have created historically over the years highly optimized stuff. Much of the work behind this thing happened at our sister campus, Berkeley, again in 80s, 90s. But at this stage, I mean, it's well taken care of. From a practitioner perspective, your company would buy these tools or license these tools rather. From a research perspective, there is more CS theory type work happening, which kind of does these optimizations and all. Okay, so okay, so that's kind of this cube kind of thing. Now, like I said, nowadays tools do this stuff for you, and in fact, Logisim has under one of the menu entries lets you enter expressions, and then it spits out an optimized expression, okay, or lets you feed a truth table and feeds out, and then it creates the sum of product of sum, those kind of implementations. So it has a very simple version. I think it can handle up to 6 inputs. Very simple version of this logic synthesis, as it is called, built into it. But go ahead.
So in like computer programs, if you're dealing with large inputs, what is like the way the computer does it? Like, is it just essentially just an exhaustive search, or does it have like actual ways?
No, it has. So again, optimally, you cannot solve the problem efficiently. So they have heuristics,
Right.
statistical approaches, and all, where over time they have kind of identified like the question at the back, could I separate things out? So is there a dimension which is more important? So I'm going to focus on that one first. Out of these, like A, B, C, D, I had 4, but maybe one of the dimensions is more important. Maybe I can factor something out to simplify my function. So they use a bunch of these finely tuned and oftentimes, unpublished internal approaches. And at the end of the day, what matters is, does this tool work faster than the other one? And that's how the marketing claim works. There is a body of research where they looked into very efficient ways of covering these things and all. And those were the work I was referring to in 80s and 90s, where kind of happened at UC Berkeley and IBM and a couple of other places, which kind of did a lot of work. So very interesting mathematical CS theory area, not much of a current research topic. So, but if you, of course, logic design was done even before this stuff, so there were certain manual approaches and all also kind of appeared. And one manual approach is a so-called Carnot map, and which is what is on the blackboard out here from the previous lecture by Professor Potkonyak. So these were developed in 60s, 50s and 60s as kind of good ways of manually approaching these problems. So what is a Carnot map? Well, Carnot map is this four-dimensional, four-dimensional Carnot map is this four-dimensional structure which has been unfolded into a plane, okay? And then there is a 3D Carnot map, 2D Carnot map. There is also a 5D Carnot map, which basically is 4 of these 4D Carnot maps. Okay, so let me tell you what these Carnot maps are. So what happens in these Carnot maps is so I'm dealing with a 4D Carnot map, which basically means that I'm dealing with a Carnot map for a function which has 4 input variables. So if I have 4 input variables, I have 16 possible values that those 4 inputs can take. So I have 16 boxes. But this map is drawn in a very particular way. So firstly, the horizontal dimension corresponds to inputs, in this example, A and B, and the vertical dimension corresponds to inputs C and D. And then furthermore, we label the rows and the columns in terms of the input value, the value those inputs are taking. So remember, the horizontal dimension is A and B. So we are labeling the first column as 0, 0, next column as 0, 1, the third column as 1, 1, the fourth column as 1, 0. And they are designed in a very special way. Can anyone think? So remember, they're not going increasing. They're not going as 0, 0, 0, 1, 1, 0, 1, 1. They're going in this particular weird fashion, 0, 0, 0, 1, 1, 1, 1, 0. Does anyone see a pattern out here? Huh? Differ exactly in 1 bit. Moreover, they differ even in 1 bit if I go from the last column to the first column. Okay, so kind of imagine this rolling around. So 0, 0, 0, 1, 1, 1, 1, 0, wrap around. Okay. It's kind of like what happens in our cube, right? I mean, they're basically corresponding to edges. 0, 0, 0, 1, there's going to be connecting them. Okay. Same thing in the vertical side. 0, 0, 0, 0, 0, 1, 1, 1, 1, 0, and wrap around. And actually, so what's happening now is, as I go from a square to a neighboring square, only one input is going to change, and the rest are going to remain the same. And actually, this neighborhood relationship is very obvious out here, but it's also true because of my wraparound. So I can go from this top right box to this top left box. That is also a neighbor. I can go from this top left square to this bottom right square. They are also neighbors. Okay, because everything. So imagine kind of this thing is that when I go through left edge, I come out on the right edge. When I go from the bottom edge, I come out on the top edge. Okay, so they're kind of connected. And then these grayish numbers that you see, they correspond to the values that Minterm is taking. So 0, box number 0 corresponds to AB, corresponds to DCBA being 0, 0, 0, 0. So that's my Minterm number 0. Or likewise, box number 7 is 0, 1, 1, 1. So that's Minterm number 7. Or Minterm number 14 is 1, 1, 1, 0. So that's Minterm number 14. Okay, and that's why you see that the Minterm numbers are also taking this weird pattern: 0, 1, 3, 2, 4, 5, 7, 8, 12, 13, 15, 14, and then 8, 9, 11, 10. So this grid structure is nothing but this 4D cube drawn in a human-friendly kind of a format out here. And when I give you a function, you can place 1 in those squares where the Minterm takes on those Minterms where the function is taking the value 1. So in particular, I can I'm just going to so this is again our same sum function we had. So Minterms 1, 2, 3, 5, 7, 11, and 13. Those are the boxes I have placed a 1, and other boxes I have a 0. Okay, which is equivalent to 0, 0, 1, 0, where I had the Minterm marked with a bubble, because that is where the function took the value 1. I'm doing the same thing out here. Now, what does an edge in my cube correspond to out here? Adjacent boxes, right? Adjacent either in column or in the row, and with the wraparound taken care of. So like, let's look at 5 and 13. 5 and 13 are adjacent in the Carnot map, and 5 is 0, 1, 0, 1, so it's out here, and 13 is out here, 1, 1, 0, 1. There is an edge connecting them. Okay. So edges mean I am either a horizontal neighbor or I'm a vertical neighbor, including wraparound. So for example, this one up here, 3, and the 11 out here, they are neighbors, because I can walk from 3 to the top and then come out at the bottom and move to 11. And you would see that 3 and 11 are neighbors out here in my cube also. Okay. What do you think face corresponds to? Box. So what kind of boxes? So 1, 3, 5, 7. So it could be a 2 by 2 box. it could also be a 1 by 4 box. In this function, it's not there, but I mean, let's imagine I were to look at 1, 5, 13, and 9. So that's 1, 0, 0, 0, 1. 5 is 0, 1, 0, 1. 13 is this guy out here, 1, 1, 0, 1. And then 15 is this corner, which is labeled out here. So there is this face which takes the marked edge of the inner cube and then kind of goes like this. Okay, I'm just if I look at this face, no, no, that's not what I wanted to do. I'm looking at 1, 5, 13, and 9. Okay, so let's imagine I had a function where this guy was 1. Okay, so 1 is this guy. 5 is 0, 1, 0, 1. So 5 is out here. 13 is 1, 1, 0, 1. So 13 is out here. Okay, and 9. Is this 9? So yeah, this is 9. Okay, so that's right. Yeah, so that is the box. So this face, if I had that face would correspond to this guy out here. Okay, if I had that. Okay, assuming this guy was a 1. If this guy was a 1, then that would be the face out here. Okay, so faces correspond to either face is either a 2 by 2 thing, and again remember we wrap around, or a 1 by 4 thing, or a 4 by 1 thing. Okay, in particular 0, 2, 10, and 8, right? The 4 corners, they correspond to a face, right? Because and you can check out here. You have 0 out here, 2 out here, and I guess the other 2 would be 8 and 10 are going. No, 8 and 10. So 8 would be this guy and this guy. Yeah, so it would correspond to this face out here. So point I'm trying to basically make is that think of this, make sure that you have the wraparound in mind as your coalescing thing. Okay, so face could be 2 by 2, 1 by 4, 4 by 1. I can combine these things. So in this human-friendly version, going back to this example, so I can start merging stuff. Okay, so playing our merging game, I can first, I'm going to look for a face. So I can merge this. Then I'm going to look, there's no more face, so I'm going to start looking at edges. I can merge this guy out here. I can merge this guy out here. Can I merge something else? 3 and 11, right? So I can merge this with this. Okay, and now I have everything covered, and there is no other. And this actually literally is what we had done earlier also with the cube structure and all. But with Carnot map, I can do exactly the same thing. Okay. Let's see any other point. So once oh okay, going back out here. Once I have merged, I can play exactly the same game. So if I'm looking in terms of expressing these things, if I'm looking at this face, A remained unchanged and D remained unchanged. So if you notice out here in our symbolism, we have also marked which columns correspond to A, which columns correspond to B, which column corresponds to D, which column corresponds to C. So, sorry, which row and correspond to C and D. So like for example, the middle 2 rows is when C is 1, which is another way of saying is that the other 2 rows, the top row and the bottom row, correspond to C bar or negative C. Likewise, bottom 2 rows correspond to D equal to 1. The top 2 rows correspond to not D. Middle 2 columns correspond to A equal to 1. So just expression A, and right 2 columns correspond to B, and you can kind of check 1, 1, 1, 0. So now when I have this face, I can basically say the face corresponds to A equal to 1 and D equal to 0. So the face corresponds to A and not D. Likewise, when I am looking at this edge, what do you think it corresponds to? Anyone? So firstly, since it's spanning a single column, so there's no merging of A or B is happening. So I have to take into account A and B both. So that is A is 1 and B is 0. So that would correspond to A and not B. But in the vertical dimension, it is spanning 2 rows, which correspond to C. So, and C. So remember, spanning 2 rows or spanning 2 columns means I get to eliminate a variable. Whereas if I'm in a single row, that means in between C and D, I have to have both present, either negated or not. And likewise, if I am on a single column, then for A and B. Let's try another one. Let's look at this merging that we did of 3 and 11. So this merging, this guy and this guy. What do you think is the expression corresponding to that? Okay, so let's see. Not C. What else? And A. Anything else? And B. Because it's a single column, so A and B both have to appear, and so we just look at 1, 1. But on the but it's spanning 2 rows, so one variable has to disappear, and the 2 rows, the top and the bottom, correspond to C bar. Let's look at finally this edge. What does this correspond to? So it's in a single row. A and not C and not D, right? Because it's a single row, which is a 0, 0, so that's not C, not D, and then it's spanning out here, so that corresponds to in this particular case, A is changing. Sorry, it would be B, not A. So B and not C and not D. Okay. So we're going to pick up this thread next time we meet. Hopefully it would be the makeup lecture, so keep an eye on that.